In this video, I'm going to go over how to throttle the gameplay of a game written in C or C++ to achieve the same gameplay rate over a number of CPUs or operating systems. So I'll go over the source code, but before I do that, I'll go over the actual environments where I'll demonstrate the actual gameplay being run and compare the speeds of the gameplay being run over several processors and several operating systems. So the first system where the game is going to be played is on the Raspberry Pi 5, which is an ARM processor, and it's running on the Debian Linux, which is the 64-bit version from Raspberry Pi. The second environment will be Ubuntu Linux, and that's going to be running on an Intel i3 core 2.1 GHz 4-core processor. And then it'll be running under Ubuntu again on an i5 Intel processor, 1.8 GHz 4 cores. And after that, I'll actually be running Ubuntu again and on the Intel i5 processor again, but this time under Oracle's virtual machine environment. And the reason I'll be doing that is because things run slightly slower under Oracle's virtual machine environment, and I'll be running the game under Windows 8 under Oracle's virtual machine environment on the same processor. So the reason I'm running the Linux under the virtual machine environment is to prove that they actually run at pretty much the same speed under the virtual machine environment, proving that the virtual machine environment is what's slowing the actual Windows 8 demonstration down. So here are all the systems running together, so you can see how they compare side by side. Top left is the Raspberry Pi ARM environment. The bottom left is the Intel Core i3 environment. Bottom right is Intel Core i5 environment. And the top ones on the left are, in the center I should say, is the Ubuntu environment. And on the right hand side on the top is the Windows environment. And because this game, Time Pilot, has a demonstration which runs exactly the same no matter how many times you run it, I can actually demonstrate how they're comparing side by side. And the demonstration for this runs about a minute and a half. And so you should see the bottom ones and the left hand side one, which is the ARM processor and the Intel Core processors, finishing the demonstration about the same kind of time. Very close indeed. And then after they've finished, which will be soon because it's just coming to the end of that particular level there, so they all come to the end pretty much exactly the same time. The ones on the top of the virtual machines, the top center is the Ubuntu one, which is about to finish now, and then the Windows one is about to finish a few seconds later, which is there. So they all run at consistent speed. So the top diagram here shows the old-fashioned traditional way of throttling gameplay on the game, and that is that when a game wants to actually display a frame, it waits for the physical hardware vertical synchronization period, and it updates the display in that period, so that when the hardware comes to display the next frame, it's already, all the data's there ready, so you don't get two halves of different frames being displayed at the same time. And it usually does that by waiting for an interrupt in the hardware, or actually polling the hardware to see when the vertical sync signal is occurring. And the bottom diagram shows the more modern way of doing it, and in the frameworks such as SDL, they will actually do the waiting for the vertical sync itself, so you don't have to worry about that. You can update the frame at any time you want, and the next vertical sync, the SDL framework, will actually time the updating of the actual physical display. But in order to actually restrict the game flow to a particular rate so that you get consistent gameplay on multiple platforms, you actually have to time how long your frame loop runs for, and then you have to pause for the remainder of that frame time once you update the frame, so that the frame rate remains as it should be, 50 Hz in the UK or 60 Hz in the US. So this diagram shows how I have to do it for my emulators. So in my emulators, I've got an emulated CPU. So the actual frame rate depends not just on the physical hardware CPU, but also on the rate of my emulated CPU. And in order to do that, what I do is I let my emulated CPU do 6,535 CPU cycles before I do a delay. because in an old-fashioned emulated CPU such as Z80, maybe you're running at 4 megahertz, or in this case for 3.5 megahertz, which is like a typical for the machines at the time, because they had that so they could actually divide down the timer to do display updates. So because if you tried to do a pause for every cycle of the emulated CPU, the amount of time you'd spend doing pauses and stuff would actually stop your the actual speed of the game so much, because you'd be spending all your time doing like, am I pausing, how long do I have to pause for? So if I do it every 6,535 CPU cycles of the emulated CPU, then I can get a lot of the running of the CPU done before I have to do any work on actually how do I restrict the flow of this actual CPU. I do this in the same way that I did, like I showed on the last diagram, in that I time how long it takes the actual emulated CPU to do those 6,535 cycles, and then I decide I take that away from the amount of time I want to actually suspend the CPU for in order to get a consistent frame rate, and I just pause for the rest of that time. And the aim is to actually do a pause so that I actually get the target frame rate of the actual emulated system. So in the UK it would be 50 Hertz, and in the US it would be 60 Hertz. So this is the actual source code of how I actually restrict the speed of operation of my emulators. It takes the clock cycles of the emulated CPU, and it waits until from the last clock cycle when it did the actual pause, which is it sets here, and it adds the 65535 clock cycles. So only after 655 clock cycles will it come in here, and it says if I'm actually configured to do a restriction on the speed. So it may be that I'm decided not to restrict the speed, and so I don't want to actually do a delay here. It gets the time of day, and this is a great function because what it do is get the microseconds of the actual system clock, and it does a difference between that and the last time it came around here. So at the bottom here after the pause, you can see it's getting the clock cycles from this particular one, so it can do a difference here of time now and the time the last time it did it. So this is measuring the time that was actually spent in the emulators itself. And if the difference is negative, that means that this value is bigger than this value. Then it just changes that to be the other way round, and then it does a yield. So this is a function I've written, which I'll go into just after I've finished this explanation, and it inverts the actual clock ticks, so that rather than the frequency, it gets the actual period of time. It takes away the difference that it just found calculated up here, so the amount of time it's spent in the emulator, and it just yields for that amount of time, so it wastes the rest of that particular frame rate time by yielding. So this is my yield function. So rather than polling, where you'd get the CPU core going to 100% CPU usage, the yield will actually sleep this particular process, and then it can go off and do other processes or sleep the CPU if it doesn't have to do other processes. I get the time of day again, so in here I'm getting the time of day in order to decide how to add the number of nanoseconds I actually want to actually sleep for, and it adjusts if it overflows on the microseconds, because the function I'm about to use uses microseconds rather than nanoseconds, so it adjusts for that by multiplying by 1,000. If it overflows the microseconds value, then it adds 1 to the seconds value and sets the microseconds back by a second. And this is where it assigns values into how long it wants to actually sleep for. And then there's this function here which will sleep a thread of execution, which is our game, or in my case my emulators, and it will sleep for however long you actually give it to sleep. And that's like an efficient way of actually wasting the time so that other processes can run, or the CPU can go into low power state if it doesn't have anything to do.